For 200 years, scientists have failed to grow a common mineral in the laboratory under the conditions believed to have formed it naturally. Now, a team of researchers from the University of Michigan and Hokkaido University in Sapporo, Japan have finally succeeded, thanks to a new approach developed from atomic simulations. Their success resolves a long-standing geological mystery and can help to create new crystalline materials. Dolomite was first described as a mineral in 1792 by Swiss naturalist Nicolas de Saussure after analyzing some rock samples collected by French adventurer Deodat Sylvain Guy de Tancrède Greatet de Dolomieu in the mountains of Italy and Austria. Dolomite, a calcium-magnesium-carbonate, forms the Dolomite Mountains in Italy, the Niagara Escarpment between the US and Canada, the White Cliffs of Dover in the UK, and is very abundant in marine sediments older than 100 million years. But curiously enough, nowadays it forms only sporadically when salty water evaporates, and it is almost impossible to create under laboratory conditions. This apparent paradox, with a rarely found mineral forming kilometer-thick deposits and shaping entire landscapes, was dubbed the Dolomite Problem by geologists. The secret to finally growing dolomite was solved using an advanced software that can simulate how atoms form a stable crystal network. Unlike previous simulations, this new approach also considered changes in the atomic structure over time. Our software calculates the energy for some atomic arrangements, then extrapolates to predict the energies for other arrangements based on the symmetry of the crystal structure, said Brian Puchala, one of the software's lead developers and an associate research scientist in UM's Department of Materials Science and Engineering. This video shows how cycles of deposition and dissolution can create an energetic stable dolomite crystal in a, geologically speaking, short time. To test the computer simulation, the researchers needed to create dolomite in their lab. After placing a tiny dolomite crystal, acting as a seed for further crystal growth, in a solution of calcium and magnesium, the researchers recreated the needed cyclical conditions using an electron beam that zapped the crystal 4,000 times over 2 hours. The beam splits the solution, which creates acid that removes the unstable spots but leaves the stable spots intact. The vacancies in the crystal structure are quickly filled by magnesium and calcium atoms precipitating from the solution, creating the rows of atoms needed to form dolomite. The dolomite crystal was seen to grow approximately 100 nanometers, around 250,000 times smaller than the diameter of a coin. Although this was only 300 layers of dolomite, never had more than 5 layers of dolomite been grown in the lab before.